For decades, simulating how molecules react to electromagnetic fields has relied on a convenient mathematical shortcut. Traditional computational chemistry assumes that when a field passes through a space, it remains perfectly uniform and straight, applying the exact same force to every atom it touches. But physical reality behaves differently. When light hits a macroscopic physical boundary, like the curved surface of a liquid, that boundary acts as a lens. It warps, refracts, and concentrates the electromagnetic energy into extreme, localized hotspots. This creates a severe blind spot in our models. Macroscopic light behaves according to Maxwell's equations of electromagnetics, while atoms move according to Newton's laws of motion. Standard software struggles to link these two vastly different scales. The physical geometry of the environment acts as a primary driver, where the exact shape of a space dictates the chemical reactions occurring inside of it. To see exactly how much this matters, we have to scale down from a typical standard chemical reactor to a single suspended droplet of water, measuring exactly 25 microns across. This specific size places the droplet squarely in the middle of the computational scale gap. It is large enough to refract incoming light, but small enough to house millions of distinct molecular interactions. At this dimension, incoming terahertz radiation undergoes a process called mesoscattering. Mesoscattering occurs when particles are roughly the same size as the wavelength of the light hitting them, causing the droplet to stop acting as a simple barrier and start functioning as a powerful optical lens. Mapping the exact geometry of the light inside this mesoscopic lens allows us to predictably steer the chemical mechanics occurring within the water. When bombarded with Bi-harmonic radiation at 2.3 and 4.6 terahertz, the water forces the waves to bend. Constructive interference at the shadow side boundary creates a massive energy spike at a single nanometer scale node. These chaotic oscillations are rectified into a persistent unidirectional orienting force. The spherical geometry of the droplet actively distills the chaotic incoming radiation into a stable, focused mechanical drive. This computational FDTD field map simulates how waves interact with the 25-micron droplet at 2.3 terahertz. The dark region at the right interior edge shows the localized intensity at this hotspot is exactly 4 times higher than the ambient energy. Physicists call this localized field concentration a photonic jet. From this highly magnified region, we can extract the exact rectified direct current field vector and mathematically apply it to our molecular models. A standard simulation that assumes a uniform field across the entire droplet completely misses this 400% power spike. To get accurate chemistry, the macroscopic field map must be coupled directly to the molecular model. We bridge that gap by taking the force vector extracted from the FDTD map and importing it directly into a nanometer-scale molecular dynamics environment. Floating within this specific hotspot is our target, a single alanine dipeptide. This is a simple, capped amino acid molecule commonly used to test computational models because of its well-understood structural flexibility. We maintain the temperature of the simulation at 298 Kelvin, and the total energy drift remains under 0.05%. This verifies that any structural changes in the molecule are driven strictly by the applied electromagnetic vector, rather than a thermal artifact or excess heat. The extracted macroscopic force is applied directly to the atoms of the alanine dipeptide, functioning like a highly specific, invisible mechanical hand pushing against the molecular structure. By linking the mesoscopic optical lens to this microscopic mechanical response, we activate what is essentially a virtual catalyst. Under the extreme, localized force of the photonic jet, the alanine dipeptide physically twists. It fights the flow of the surrounding water and snaps into a locked, rigid orientation. In its natural, unaltered state, this molecule fluctuates evenly around a balanced racemic center, meaning it spends equal time in left-handed and right-handed structural geometries. This chart shows the probability density of the molecule's improper dihedral angle. The red dashed line marks the ideal racemic center at 0 degrees. The molecule's structure has been completely forced into a fixed 125.86-degree twist. The solid purple histogram peaks on the far right show zero overlap with the control state over the entire 1 nanosecond trajectory. The molecule never returns to the center, demonstrating a state of complete enantiomeric lockdown. We can predictably force a specific chemical orientation by utilizing the physical shape of a water droplet. Coupling macroscopic field maps to atomic physics transitions this concept from theory into a rigorously validated blueprint for manufacturing specific chiral molecules using nothing but the precise geometry of light.